Good afternoon, everybody. My name is Aditya, and I am the project manager of team number 2 for data structure CIA 2. And today, our topic is VEB tree and Treap in the data structures project. And here are our team members: Dharnish, Gangesh, Sanjit, Abhishek, Shashank, Jyotiraditya, myself, Tanya, Manya, Ansh, and Gary. So for today, we have Dharnish and Sanjit, who are the developers of this project, one of the developers of this project, who will be presenting the topics respectively. Dharnish will be presenting the VEB tree, and Sanjit will be presenting Treap. And over to Dharnish.
Yeah. Hello everyone. I'm Dharnesh and I'll be presenting the VB tree. But before we go into the actual code behind it, let's just discuss what a VB tree is in theory. So Ansh, can you start screen sharing? Yeah. Okay. Yeah. So hold on. So what is a VB tree? So a Van MD Bose tree is basically it's a more optimal and more advanced data structure as compared to regular search trees. So you all are familiar with how binary search trees work, right? They have an they have a worst case time complexity of overlog n, and they are pretty efficient at what they do. But there are some inherent disadvantages which VB trees tend to solve, and this is because their entire operating they're basically operating in a universe. They assume that they're operating in a universe of variables, where the universe consists of only integers ranging from usually 0 to u minus 1. So by doing this, they basically divide the entire universe into multiple different sub-universes, where each universe is basically can be thought of a cluster which has a minimum value and a maximum value. So these minimum values and maximum values make it extremely fast and efficient to basically identify, search or insert or delete any element from a given cluster. So the worst case time complexity in this scenario is basically O of log n, where n is basically the size of the universe. So these are some of like the advantages of what a VEB tree are. So now we can go now. Yeah. So let's talk about the clusters that we were let's talk about the clusters. So basically, a cluster is basically how the universe has been divided. So when you have a universe of integers, the clusters are basically subdivisions or even subsets of a given universe, where the size of the cluster is usually defined by the square root of the universe size. So they usually have a summary. They have a summary element which is basically used to track the minimum and maximum values of each of the individual clusters and update them whenever you're inserting or deleting elements. Yeah, so I think we can probably move down. Yeah, okay. So now, as I mentioned before, the insertion and deletion operations in VB trees are highly efficient because of this division of the universe, where basically it's basically a divide and conquer problem. You're essentially dividing the problem into half and half and half, which makes it extremely efficient and extremely fast at its job. So you can literally insert elements at O of log u, where the u is the universe size, and deletion can also be performed just as efficiently. So we can move down, I guess, now. So let's now talk about some of the inherent advantages here. So one of the main draws of a Van Boas tree is its efficiency, because it's able to insert and delete elements at an incredible pace. In fact, it's actually way exponentially faster than most of the common data structures that we have been used to, and it's also immensely scalable. General use case that I've generally seen is it's generally used in modern networking routers, where you're given a given IP address, and basically the ranges of IP addresses where it's supposed to forward those IPs are generally clusters. So by using a vanity Bose tree here, you're able to essentially increase your efficiency and your power savings as compared to normal data structure implementations. So yeah, I think we can go down. Yeah, as we discussed, the time complexity is incredibly fast. However, the space complexity is where it kind of gets a bit murkier, since you're basically essentially dividing your entire universe into multiple different sub-universes. Each universe tends to take up its own space for initialization and all of that. And as a result of that, and in addition to that, we're also using a recursive structure to figure out what the possible elements are for finding like the successor or predecessor and all of those. And because of that, that it inherently means that you're going to have a higher space complexity. So I think we can go down. Yeah, so these are some of the main advantages that I discussed before. One advantage which I haven't discussed till now is the potential for parallel processing. Because in a VB tree, right, you're able to process multiple elements because the universe has been divided into multiple different sub-universes. There are multiple different clusters. So it allows for more parallel processing as compared to a usual binary search tree. What happens in a normal binary search tree? You're essentially just taking an element, you're inserting it, you wait until it gets inserted, and then you move on to the next element. But in a Van Emde Boas tree, it's essentially multiple different clusters, right? So you can literally just do all of them simultaneously, and it will allow you to gain the efficiency that I was talking about earlier. So yeah, I think you can go now. Now let's talk about some of the considerations and limitations that we need to take into consideration. So some of the limitations are that it's inherently complex to implement. There there are many different like problems associated, and it's generally hard to implement because of its complex organization. So in a normal binary search tree, it's really simple, right? You have a node which points to the right and which points to the left. So that's inherently easier to implement. However, in a randomly burst, you need to account for the universe size. You need to ensure that the numbers you're trying to insert are not exceeding the size of the universe. That can cause undefined behavior. So there are inherently more limitations, and it's also just harder to implement into existing systems because most modern systems are using traditional data structures, and trying to integrate a randomly burst tree along with them, it becomes really hard. And the second thing is adoption and awareness. So there's actually a surprisingly less amount of awareness regarding the vanity poetry. Uh, a funny example is that we were actually researching for a lot longer than necessary for this because we weren't able to find any information on vanity poetries. But yeah, so and also since it's not really that it hasn't really propagated as much. It's harder to convince companies to integrate vanity poetries into their daily workflows, and also it's inherently harder to implement. So that's kind of it for the limitations and challenges. I think we can move on. uh, yeah, so now let's just have like a brief just a summary of what we've discussed till now. So what we've seen till now is that a randomly BuzzFeed is exceptionally good at performing multiple operations in parallel. So insertion, deletion, or searches, it's extremely efficient. But the problems that it usually has are that it's more complex to implement, and it has a higher space complexity. So you need to account for that. And also it has the awareness about it is extremely low, and that's also a major weakness that it has. But however, more there are actually increasingly a large number of processes or programs are increasingly relying on parallel processing. So I guess if randomly tree can take advantage of parallel processing, it could actually be a really big game changer in the coming years. And also, some of the threats it faces are from the traditional data structures, which are much easier to implement and are more widespread among companies. So that's basically it. Yeah, I think we can go down. Yeah, okay.
Thank you,
So
Darnish. So next we have Sanjit, who will be giving us his views on Treaps and his work on Treaps that he has done during this project time. Over to Sanjit.
Yeah, so now we have basically discussed about van and Boas trees, which are a fairly complex data structure, as we all found out when we are trying to develop it. So now let's scale it down a bit and let's go to something a little more common and a little more simpler called trees. So basically, what is a treat? A treat is nothing but a type of a self-balancing binary tree, which also maintains the properties of the heap data structure. So basically, it's a binary search tree which maintains all the properties of a binary search tree, that is O of log in searching, O of log in deletion, O of one maximum and minimum, and O of log in traversal. But at the same time, it introduces some new things like randomization and the key concept. So basically, in other types of self-balancing trees like AVL tree, um, red and black tree, there's a certain algorithm which we have of the left and right rotate so that we can get the tree in a balanced structure. But what treats do is that we use the randomization property. So in the tree, there's a random priority assigned to each node, and according to that priority, we do the balancing. So we can go down. Yeah. So we basically discuss these, so we can go down again. Yeah. So basically, what this randomization property helps us in achieving is flexibility. So basically, Treaps can be adapted to many different applications, such as connectivity problems, range query problems. Treaps can be used for many other things as well. So like the number of scenarios it can be used in are endless. And since it maintains all the properties of a binary search tree and a heap, it's also very efficient. As I said, in overflog in time, it can do searching, insertion, deletion. You can go down. Yeah. So I guess we've already discussed this. So you can go down again. And yeah, so basically, one use of Treap is database management system. It is actually quite frequently used there. So basically, like Treaps can play a crucial role here because of the parallel processing capacity, the data sorting capacity, and the optimized algorithms. So like there's indexing and retrieval where the Treap can play a crucial role in like managing the database system, and particularly in indexing the data and like retrieving the data from a very large database. The randomization helps to like reduce any errors. Then query optimization, like Treaps can contribute to query optimization due to their search efficiency in databases again. And then lastly, Treaps are scalable in their performance, like can be scaled to like really large systems as well, which makes them an ideal data structure for developers. And we can go. Yeah, so these things we've already discussed. One thing that we should note is that unlike the AVL trees or red-black trees, which guarantee balance in all cases, since trees rely on random priorities assigned to nodes, this means that the worst case performance can be skewed a little, but the chances of this happening are quite low. And despite all these advantages, and even though it's really interesting theoretically, they've not gained like a lot of widespread adoption, just like the Van Embe Boas tree. So now we can go to the code for this before we discuss the code for the Van Embe Boas tree.
Thank you, Sanjit. So for this project, we have two separate code implementations of PEB tree and Treap. So our team for the developers was divided into two. One that was on the VEB tree implementation and the other one that was on Treap implementation. Now we will look at the VEB tree implementation, and we are currently using an online compiler to show the output. And Dharnesh will be taking on from here. Dharnesh.
Yeah, okay. So before we actually run the code, let's just go through what the code does and just get a kind of idea of what it does. So basically, initially we're creating a class called VEB tree. So this class is basically just a class which defines a normal VEB tree where it has a universe size. So this universe size is actually important. Basically, it defines the range of possible keys that you're allowed to insert. So any key which is basically higher than the universe size cannot actually be inserted. It actually can be inserted, but it generally tends to result in undefined behavior. So we try to ensure that we're not exceeding the universe size when we're inserting an element. And we also have a min and max. So this min and max is basically defined for each individual cluster. When we divide a universe into sub-universes, the min and max is responsible for basically defining the minimum and maximum values in a given cluster. And the summary basically keeps a track of the min and max for all the different clusters. And so we also have a high and a low. This is basically used to basically demarcate the bounds of a given cluster. And the indexing is also similar to that. And for that, we basically just use the square root of the universe size. And that's basically it from here. And we have an insert function, which is basically just, it basically checks if if the tree is empty. And in case it's empty, then we just insert the element and the minimum and maximum is equal to X. So this is where now we'll move on to the actual constructor. So when we're actually creating an object of this class, there's two main things we need to look at. So the size and the minimum and maximum. So we're gonna check if the universe size is actually greater than two. If it's greater than two, then we are allowed to create multiple different clusters. And when we're creating a cluster, we use the square root of u to actually define the size of the actual cluster. Right. Okay. And now here we're just creating a summary of that. The summary is basically just another random Boas tree, and we're also having a destructor to basically deallocate memory after operations are done. So now let's actually move on to the insert function. So insert, as I said before, it basically checks if the tree is empty. And if the tree is empty, then it basically just calls insert empty. In that case, you know that the minimum and maximum are going to be X. So it basically does that. And then after that, what it does is, in case it's not like that, it's basically just going to insert the value and check whether it's the minimum or the maximum. In case it's the minimum, it'll basically just swap. We have a swap function for that. It'll swap the values and essentially just give you the minimum value at that particular point in time. So, and after that, we're just going to define the cluster size. So the cluster size is basically just going to be updated according to minimum and maximum. So that's basically, it's essentially the same thing, same process that we're doing in deletion. But in deletion, what we're going to do is we're going to have to identify what the cluster is. We're going to have to find out which cluster the element actually is in. So there, we're actually just going to be like, we're going to check each and every individual cluster. So for that, we're just using in the first cluster, and we're going to basically just move on to the higher points of each different cluster to figure out if there's a point at which the cluster is identified. And in case the cluster has been identified, we basically iterate throughout the cluster and we figure out and we basically remove the element from that given cluster. So I think we can move on from deletion. So those are all just the operations of deletion. Now let's move on to successor. So for successor and predecessor, it's essentially the same thing that we were doing before. It's basically a search, but here what we're doing is we're initially just checking off the base conditions here. So we're just checking if u is equal to 2, and we're checking if it's empty, and we're basically updating it if necessary. So when we check for a successor, we basically follow the same steps, but instead of basically deleting a given operation, we basically just iterate to one element which is before the given element in a cluster. So once we're done with that, we basically just return the successor that we get. So that's basically the successor, and the predecessor is basically the same thing. So yeah, I think we can move down. Yeah. So the maximum and minimum basically just return the given maximum and minimum value which we've been updating throughout the operation of the tree, and we basically just return the value. And the printing just prints out the different nodes in a given tree. So now I think you can actually move on to actually like running the code and see, showing you the final output. Yeah, so as you can see, we've defined the universe size here as 16, and we've inserted five different keys into the pair. And notice that all the keys are always lower than the universe size. So that's an important consideration that I actually didn't mention in the presentation, but it's something you have to keep in mind. So now you can see after insertion, we basically we get two and 10. We get all of these nodes. All the nodes that we had to insert, we are getting it 2, 3, 5, 7, and 10. So, and after deletion also, you can see that we've basically removed 3 out of the equation. And we can also see that the successor of 5 is 7, and for 7 it's 5. And we're also getting a maximum and minimum values as well. So that's essentially how a vanity Boas tree works, and this is the working implementation of it. So that's all. That's it from my side. I'll be handing it over to Sun to explain his code.
Right. So
Thank you,
moving
Danish.
So moving on to the Treap code, first we define the structure called Treap node. So basically, the node in the tree, it has the key like any normal binary search tree. The different part comes here when we have the priority, and then of course the left and right to maintain the tree structure. Then in our class, we are simply assigning a root node, and so that we don't have to call it in the main function. And we're also assigning the root to null. So our void, push, and pop are basically just applications of an insert and delete function. So we can skim over those and go to top. Okay, so yeah, can you scroll down? Yeah, so our top function is also simply just seeing if the root exists or not. So and empty is the same. So now coming on to the main part, which is our insertion function. So basically, how it's called insert util here. So basically how that works is that it's a function to insert a new node with a given key into the tree. So if the root is null, that is the tree is empty, then you just simply create a new node and assign the root to it. Otherwise, we'll recursively insert the new node into the tree using the binary search tree property. Then after we insert it, we check the priority and then perform the right rotations and left rotations in order to maintain the balance of the tree. So then next we have in-order traversal, which basically we are just visiting the subtree, printing the node, and then visiting the right subtree. Delete key is again just a implementation of delete util, so we can skip over that. And yeah, so Treap star new node. This is again just to create a new Treap node with a given key. I believe we call it in the other function which I just displayed. So it assigns a random priority value to the new node because this randomization is the key property of a tree. And then we assign the left and right child pointers to null, right? So then we have the next major part of the code, which is the right and left rotate. So basically, all this does is it performs a right rotation of the tree. So it takes a node as an input, rotates it to the right, and then returns the new node. So basically, we will use this to balance a tree. Left rotate is the same thing. And delete max util is basically just a function to remove the node with the maximum priority. So we just recursively search the tree for the node with the maximum priority, and then we just remove it from the tree. And deletion, we are actually searching for the specific key. So it's the same thing as delete max util, except here we're not searching for the maximum priority, we're searching for a key. Once we find the key, we delete it, and then we simply do the necessary processes required to balance the tree again. And then lastly, we have our test function. So basically, we are implementing a priority queue using our Treap. So basically, this is just to check whether we can actually implement that. So we have our keys given in an array. We are pushing the keys. We are like making new nodes in the Treap for each key. We're randomly assigning priority, and then we're trying to prove that the priority queue actually works, and we are popping out according to the priority queue. So we can run the code. Actually, before we run the code, just show the main function. Yeah, so here we are assigning the random probabilities in case you were wondering. So now we can run the code. Right, so as you can see, it's showing us the priority for each node inserted. Then it's showing us the delete works by doing in-order traversal twice, once before deletion, once after deletion, and the nodes are correctly being deleted. And then we are doing a priority queue property, which is popping according to priority. And as you can see, the greatest priority is pop first, and then it goes in descending order. So that's all from this side.
Thank you, Sanjit. Thank you, Darnish, for giving us the presentation on both the topics. So before we end this discussion, I just wanted to tell about the contributions that each member has made for the team. For the developing, we have Gangesh, Sanjit, Dharnish, Abhishek, and Shashank, who have been divided into two different teams, as since we had two different topics. And we have Gary, Tanya, and Manya for the testing, who did testing for both the topics once the developing was done. And I myself am the project manager, and Ansh is the business analyst, who was responsible for the applications of the both the topics and also the presentations that were made for today. So thank you.